Okay. All right, we're ready. We're going to move on from trusses. I didn't see any questions about trusses pop up, so we're just going to jump right into the next thing. If you do have a truss question that we want to look at, then I guess put it in the chat, and I'll see if I can pull it up the web work for that and look at it. But I didn't see any questions about it. So what we're moving on to is this topic called centroids. So centroids are a piece of the equation when we get into calculating some of our stresses for next not next quarter, the next third of the middle third of the course. So like after exam one, we'll need these centroids, but we're going to go ahead and start dealing with them. You can kind of look at the word centroid and you've sort of got center in there. And centroids do have to do with the center, or at least sort of the center of a object. We are only going to do two-dimensional centroids. You can you can have three-dimensional centroids, but we're going to think of centroids of just two-dimensional shapes. So like the cross section of some beam, and we want to find the centroid of it. So the general idea is that if I had a beam, well, let's go to OneNote and let's draw some stuff. Let's see, here we are. So let's just do one that's really straightforward first. So I've got a rectangular cross section, and this is a beam. So we're gonna have something like this. Let's just quickly make us a little. Whoops, I wanted to move that one, not. Oh, there we go. That one, and there, and then we'll put some lines. So we got a rectangular beam back here. Don't need that part. And the cross section of this beam is just a rectangle. So this is our actual beam. You wouldn't really often have a square beam like this in a bridge or whatever, but you might. And it might be a tube, it might be an I-beam. We'll talk about all these different beam cross sections later on. But for now, we just got this square-shaped solid beam. It's really short looking in our picture, but that's okay. The cross-sectional area of this thing is just going to be the rectangle, right? So anywhere I cut across, so if I take some plane somewhere, that's going to be hard to figure out what's going on. Maybe if I erase that part of it, where it goes behind there. Something like that. So, this would intersect maybe, I don't know, it's kind of hard to tell where it would intersect, but maybe right here and here. And then I would have these, I'll just draw these kind of dotted lines back here. So anywhere I move that plane, the cross section in this particular beam is going to be just a rectangle. That's not always true. There are maybe tapered beams or beams that are curved in some way or shape that where as you move down the length of the beam, the cross section does change. We are not dealing with those kind of beams in this course. So these are just beams that they're not all rectangles, but whatever cross section they are, it's the same throughout the entire length of the beam. So anywhere you chop it with this little green plane that I've drawn, anywhere you chop it, the cross section is going to be the same for that beam. So for this particular one, the cross section is just a rectangle. Sometimes you have cross sections and they have like cross hatching on them, like this. You don't always, and actually I won't often draw the little cross hatches on it. I'm just kind of doing it right now to get our names of things and everything under control. So there's our cross section. Maybe this beam really looks like it needs some dotted lines back here to kind of make more sense. That might make less sense because it's got all these lines everywhere now. But the idea is that we want to find the centroid of this cross section. And for our course and for our assumptions, this cross-section doesn't change throughout the length of the beam. So the centroid is, if I took this cross-section, like cut it out of a sheet of thin plywood or whatever, and laid it down flat, the centroid would be where it would balance at. So if I like took the plane and put it on a little post, it would balance at the centroid. So for our rectangle, that's why I chose a rectangle, is because it'd be really easy. We can just look at it. The centroid is, right there in the middle. A lot of times you take and put some kind of axis here, and you say that this distance from some reference, in this case I put the reference axis down here at the bottom, and I could put another reference axis kind of up here for the y-axis, and we just say that, oh, well, this distance is y sub c. So it's the distance from my reference axis, in this case x, in the y direction and going up to the centroid, so y sub c. I would have x sub c would be the distance in the x direction between wherever my y-axis is and the centroid. In this case, x sub c is 0 because I put the centroid right on top of the y-axis. And so that sometimes that's true. And so those are just terms that we'll get into. We're going to back up a little bit now and develop a little bit of idea of where this centroid comes from. Then we'll go into calculating this centroid, and then we've got some examples to do. So let's back up from this point a little bit and abstract out what we're doing here. So let's start with a coordinate system. So there's an x-axis and there's a y-axis. So the centroids do have to be measured in reference to some kind of coordinate system. Typically you get to choose where that coordinate system is located, but if you're solving a problem like a homework problem or exam problem, that axis will be given, or it'll be shown, or somehow you'll know where that reference is. Otherwise you could correctly calculate it, but according to the wrong reference. So on homework problems and exam problems, the reference axis, like I've got here, is just given to you in one way, either in writing or it's shown on the picture or whatever. All right, let's make a really simple system, but not like a rectangle, something that is more generic. So let's say that I've got a circle here, and then let's put another one over here. All right, and so these are like little spheres or something. What I'm going to think of these as these are little pieces of a bigger part. So in our rectangle, they might be a little piece here and a little piece here or whatever, and I could fill in that whole rectangle with a whole bunch of these little circles if I wanted to, or these spheres if I wanted to. But I want to abstract away from the idea of rectangles for a little bit. So we just have random masses. They don't even have to be circles. They could just be blobs. Each one of these has its own weight. So this is sphere 1, so this can be weight 1. And this is sphere 2, so it can be weight 2. So it has, each of these has their own weight associated with them. And these can be infinitely small, right? They can be super tiny. I've drawn them where you can see them, though, so that they're not unseeable, but that's kind of our idea. Also, they both exist in space somewhere. So they have coordinates. So they have x and y coordinates. For now, I think I will just use the x coordinates. So this, measuring from the y-axis over to sphere 1, that'll just be x coordinate 1, whatever that number is. Same thing over here, except it's a 2. And both times I'm measuring over to my reference y-axis. So I do have to have this reference point. If I were doing the y coordinates, then I'd measure from the x-axis in the y direction to get y1 and y2. But I don't want to cloud it up too much right now. All right. So what I want to do is I want to develop some system where no matter how many of these little spheres I have, infinitely small, scattered everywhere, that way I could arrange them in any shape I wanted, right? So I could arrange a whole bunch of these things and make a rectangle or a T shape or any kind of shape I wanted to make. So if I can figure out some rules for how that would work, then I can could deal with any shape possible, which is what I want to be able to do. I don't want to be limited to rectangles for every centroid I want to calculate. So what I want to know is if I have some number of these spheres, in this case I have 2. So I only have 2 because I want it to be very simple. But I could have 2 million of them, and it would just take me a whole lot longer to draw all these little x1 through x1 millions, and a whole bunch more to do. But that's what we have calculus for, is we come up with some rules, and then we use calculus to expand them into this infinite space. So here's my idea. Somewhere I know that this pair, they're not even touching right now. I've got x1 is completely separate from x2, but I could have drawn them touching each other. I could have drawn a whole bunch of these things and filled in the whole area. But somewhere I know that there is a centroid that represents both of these things. So, I don't know. Just looking at it, it looks like, well, it's probably right in here. And it's somewhere in there, and it's labeled. I'm going to move that W1 because it looks kind of weird right there. I'm going to put it up here. So this is X sub C. So somewhere there exists a centroid of all of the little spheres I've drawn. And I know that that centroid exists at a distance X sub C, because X sub C is the X coordinate of the centroid. And I just labeled it on here. I also know that this centroid has some weight of its own. I'll call that W sub C for now. All right. So all of that is, I'm just defining things, nothing magical here. When I talked about this guy, I talked about the centroid of our rectangle being the point where it would balance. So it has something to do with the weight of the shape, right? And I do have weights here, weight 1, weight 2, weight sub C. So the idea is that when something's balancing, it's in equilibrium. And maybe if we do this, let's see, let's just draw a little beam. You've played on a seesaw before, and there's a weight over here and a weight over here. We'll call that just A and B. And I can figure out if this thing is going to balance. You can do it by sitting on the seesaw, and sometimes you're the heavier person or the lighter person, and if you're the heavier person, you've got to move kind of closer towards the fulcrum, the pin in the middle, so that it balances. If you're the lighter person, you got to be way out on the end of the seesaw to make it balance out, right? So that's a moment. Remember, a moment equals a force times a distance. So A, person A over here times their distance, we'll call that dA, should equal person B times their distance for it to be in equilibrium. That would be the summation of moments about, I'm just going to call it the fulcrum, equals 0. Let's do clockwise positive. And let's just say that means that B times dB is going to equal A times dA. So I'm just doing a summation of moments. I could do the same thing with these little spheres, because each one of them has a weight that they're associated with, and they have a distance from my reference. Now, it might look a little weird because, you know, I've drawn this in 2D and it looks like the weights are, if I had thought about them creating a moment about the y-axis, then, you know, is it clockwise, counterclockwise? I don't know. Which way is it going? So it might be a little bit difficult to figure out what's going on here. But if you imagine that these weights are in the XY plane, the spheres, they're in the XY plane, and the little red arrows are actually into the screen direction, then you could start to see how sphere 1 could create a moment about axis 1. So it's kind of orbiting axis 1, right? So if I take that idea and I say that the W1, so the weight of sphere 1 is pointing into the screen, times however far it is from the X, or well, from the Y axis in the X direction, however far that is, plus W2 over here is doing the same thing. W2 times its value or distance from the Y axis, X2, has to be balanced by this WC. So WC is this imaginary thing that I made up. I made a very rough one so that we're not confusing it with the spheres here. But it's kind of like the centroid of whatever group I have. So right now I just have a group of 2 spheres. What I want to be able to do is take any shape sphere, any number of spheres, the little nice neat ones that I drew, arrange them in any pattern I have, and find the equivalent thing that is this centroid. So I want to find out, basically I want to write this Fulcrum equation over here. You know, I want to do something like this, but with these little spheres. So W1 times X1 plus W2 times X2 plus Wn times Xn, all of them I have to equal what I've called Wc times Xc. So what this says is that, all right, I've got all of these little spheres that create the pattern of my cross-sectional area, whether it's a rectangle or some weird shape. And what I want to do is I want to basically condense that down into one weight, Wc, at the centroid. Wc is the weight of this equivalent thing, so it's actually the total weight. So Wc is actually equal to the total weight of all the spheres in my group, which in my case is equal to W1 plus W2, because I only have 2 spheres here. But it's as many of them as I want. And what that will do is give me this equation. So W1 times X1 plus W2 times X2 equals the total weight, so all of the little individual spheres added together, times Xc. What I want to know is this. This is the coordinate of the centroid for this whole group. So I just solve it. X sub c, ooh, let's not write it in yellow. X sub c, the location of the x coordinate of the centroid of the group, just equals W1 times X1 plus W2 times X2 over the total weight. Now, what if I had, 2 million of these spheres? I don't want to write out this like this, so I would generalize it to X sub c equals the summation of all of the W's times their x coordinate divided by the total. Well, I could do it 2 ways. I'll just do weight total, which could also be the summation of all the Wi's. So we could write it that way. So R this way. Like that, right? So now I've got a digital way to do this. I can literally go and add up every little sphere, multiply it times its x coordinate, divide by the total weight, and I would have the location of the group's centroid. So that's what I would have. I can make it a little bit simpler than that because of some of the stuff that we said back here. So in general, and for what we're going to do in this course, let's say that weight, yeah, we'll put it, maybe we should put it down here, since we're talking about weight down here. Weight, so this is in general. So that we can make our equation a little bit simpler. Weight equals mass times g sub c, right? So gravitational acceleration, g. For pretty much anything that we're going to deal with, g sub c is a constant. Like, we probably don't have this rectangular beam where one end of it is in a place with one gravitational constant and the other end of it is in a place with a different gravitational constant. That'd be really unusual. You know, maybe if we're doing it in a space elevator or something, then we have to deal with that. But for most of the stuff that we're going to build, g sub c is constant. So that's good. That's constant. Also, density for, let's say, this guy, this little beam, we've made this beam out of some metal. In general, not 100% true, but in general, that beam is the same density from one end to the other. Like, it's probably not changing in density. You could force it to change in density, and there could be a little bit of randomness in there. Maybe one end is a little bit more dense than the other end, but it's generally constant. I'm going to say beam here. This does not only apply to beams, but a lot of what we are going to use this for is beams later on. But it doesn't have to be beams. But for metal parts and things like that that we've made, probably they have a consistent density. You could think of some situations where that's not true, but in general, it's true. Also, density equals mass over volume, right? Whoops, that's not a V. Right? So we usually use rho for density, m for mass, and volume. We could say volume is whatever the cross-sectional area is times the thickness of the thing. So if we look at this guy up here, the cross-sectional area would just be the green little square, and the thickness would be this dimension. Right? So if we took that the green crosshatch square area multiplied times t, we'd have the volume of this rectangular beam. All right? Now, for, again, just how most of our beams that we use don't change density from one end to the other, a lot of times the area is constant, right? We already talked about that, where this is a square from one end to the other. It's not a square on one end, and as it gets to the other end, it's a triangle. I mean, you could do that, but it's typically not. So area is constant. So what I'm ending up with here is a lot of variables built into this thing that I've called weight that are actually constant for our beam. Density is constant. G sub c is constant. The area doesn't change over the thickness of the beam. And what that ends up doing is saying that area ends up proportional to mass. It's not equal to mass, but it's proportional to it. Like, it's a linear relationship between them. And this A, just so we are sure, is the 2D cross-sectional area of our object. If some of this is like, why are you even talking about all this? That's fine. This is really just to get you some background, because what we're going to end up doing is very like cookbook type of stuff. And if you just start out with just the cookbook stuff, you're kind of limited to only doing the cookbook stuff. So we're going back to why you're able to do the cookbook stuff And then if you ever need to do something other than just look up a thing in a chart somewhere, then you'll have a little bit of background on, okay, that's what that's talking about. Or you'll know that, I do have one of those beams that is tapered and I can't really do the same thing. I've got to do something different than just the cookbook. In this course, for the homework and problems like that, the cookbook thing is going to be fine. But you need to have the fundamental stuff behind it so that you know when that works and when you have to do something different. All right. So let's see. We've got our area proportional to mass. So what that lets me do is, it seems weird, but how I had this weight up here, I was using the weight to kind of create this moment about the y-axis, or we could have done moment about the x-axis if we wanted to find y sub c. But since for real situations that we're going to deal with, g is constant, density is constant, area is proportional to mass, it lets me take out weight. I don't have to worry about weight. And only thing that really matters is the shape of that cross-sectional area. So it lets me take this equation here with these summations. Don't worry about weight, only worry about the shape. All the stuff that the area times all the g and t and all that, the g and t, they're all constant, density's constant. So it's only the shape that matters. Again, assuming all of those things that we talked about being assumptions are true. It lets me write x sub c equals the summation of ai times xi over the summation of ai. All right, I think we're back now. It looked like it had a little internet problem, but I think we're back. All right, so what I was saying is this numerator here that's on the screen is the first moment of area. And that seems weird because moments are forces times distance, and we're talking about area times distance. So it gets a special name, first moment of area. Later on, we'll do a second moment of area. And it's a little bit different. But just know that it is okay that we're multiplying an area times a distance and calling it a moment. And that works because of these assumptions we made where the area is the thing that's changing, or well, not changing, but it's the variable. Density is constant for this beam. The gravitational field is constant, all that kind of stuff. And all that the weight depends on is those constants multiplied and divided by whatever shape I'm dealing with. The other thing I can do is I can say, well, that's fine. Before I go too far, let's also just write, I didn't do any of the y's. What this y equation would be is the same thing, except I would be measuring, instead of x1, I'd be measuring y1. So the distance from the x-axis. But everything else would look the same. So y sub c would equal summation of ai times yi over summation of ai. And y sub c would be the location of the centroid of the group of little spheres, which now the spheres, we do have to imagine there being so millions of spheres that they can be combined together in any kind of shape that I want. And that would be the location of the centroid in the y direction. So that's good. We're going to come back to those. We're going to generalize these a little bit further and say that, well, if I can do a summation, then I could do an integral. So x sub c equals the integral of, I'm going to rearrange these here. So x sub c would be the integral of x dA over the integral of dA, which is just the total area. So I would take, and we'll do this one in a minute so that you can actually see it in practice, but this represents the same thing as taking all the individual little spheres and multiplying times their moment arm, x, and then same thing for the y. So y sub c would equal the integral of y dA over integral of dA. So let's see how these work. So let's take, let's go to MathCAD for this, I think. Where did I put MathCAD? All right, there's MathCAD. Yeah, y'all see MathCAD. All right. So let's create a function. I had one picked out. Y of x equals, I did 3 times x squared plus 5. I think, yes. Now these would have units. We're going to ignore units for now, but obviously if this is going to represent some kind of physical shape, then it has inches or meters or millimeters, something. We're going to not use units right now. Oh wow, let's see, I haven't plotted something in a long time. How do we plot? Let's see, plot, insert plot, xy. We're going to use y of x on the x-axis, and we'll use, we'll use x on the x-axis. So there's our shape, just a little parabola thing. Let's say that we are trying to create, I can't draw in here, can I? Nope. All right, let's go over here. Actually, we'll just take this real quick. Let's do a screen. So we got this guy. Put it over here. All right, make it a little bigger. All right, so this is the entire equation. Remember, this equation was y of x equals 3x squared plus 5. That's this curve. Let's say that this represents, we're going to go from 0 to 3. So, oh, well, yeah, that's fine. 0 to 3. So this little guy right here is our cross section. So this would be a beam that looks like this. And then it's, you know, it's got some length to it. So kind of a weird shaped beam, but maybe that's what you need in your design, is some weird shaped beam like this. And you need to find its centroid. Now again, we're talking about not the centroid of the beam, but the centroid of the beam's cross section. So the centroid of the beam, you know, the beam is a three-dimensional element, so it would have a place where it would balance to, somewhere in here. We're only talking about the centroid of the beam's cross section. So just this little piece. Anywhere, and it doesn't have to be on the end of the beam, anywhere I chop this beam, just like I did up here with the little green plane, I could move that into and out of the beam. Anywhere I chop it, I would have this little cross section, which is defined by this curve, the area under that curve, right? So I could define some random shape. I could create any function to create whatever shape I wanted. Most of the time we're working with beams, they're probably like rectangles combined together, so we'll deal with that later on. But this is for the purpose of you know, figuring out what we've got going on here with any shape. So we'll get to rectangles a little bit later. All right, so I'm going to take just this little piece that I've kind of shaded in and draw it bigger so that we can deal with it easier. Whoa, that did not create a straight line. There we go. So there's our x-axis. We'll put our y-axis somewhere up here. We're going to measure from, I said this is going to go from 0 to 3 inches, we can call it. So we'll put 0 right here, and we'll put 3 somewhere over here. And looking at our little shape, I'm not too worried about the actual sizes. Well, I mean, I am, but I'm not too worried in my drawing about the actual size. But let's just say that 3 is here, and then it's going to go up to here. So something like that. So there's our little shape, bounded by the x and y axis and these curves here. So the top curve is controlled by our equation. And the other side is just controlled by, I chopped it off at 3 inches and at 0 inches. So instead of having, you know, this entire curve. I'm only dealing with this one little section of it. All right. Now, what I want to do for solving this equation, let's just do, which one did I do? I think I did x sub c. All right, so our equation, x sub c equals the integral of x dA over the integral of dA, and it's going to go from 0 to 3 because that's the psi, as I said, in the x direction. And I want to integrate this. So I've got to figure out what dA is. So when you integrate, remember you're calculating the area under the curve by dividing it into really narrow little strips and adding all those strips together. That's what integration does. So I'm going to draw a bigger than normal strip just so we can see it. But that right there, that could be dA. Right? So that guy's dA. And I have a whole bunch of these. Let's draw some more. I'll draw them this way. So, you know, there could be another one right here. Another one right here. And so forth and so on, you know. You make them really thin. I'm not going to draw all of them. That's enough of them. So there we have all these little strips. Now, to make them really thin, I give them a special width called dx. Right? So I give them this little dx width. Their height is this guy. Their height is y of x. So 3x squared plus 5. Okay? So dA, the area of the little integral strip that I'm working with here, equals y of x times dx. That's the way I would calculate that area that I shaded in blue. I would take its height, multiply it times the base, which is y of x times dx, and that would give me dA. So now I can re-look at my equation. X sub c equals integral from 0 to 3 x dA is now y of x dx over the integral from 0 to 3 dA is y of x dx. Okay. The x coordinate for this little strip is this guy. I'm measuring from the y-axis now this way back up here. I use spheres here, so I measured to the very center of them. I measured to their centroid, in fact. So the centroid of this little sphere was right in the middle of it. So I should measure also to the centroid of the little strip that I'm using, which, you know, it's right there. So x is that distance. I am not going to do x is equal to any kind of like some distance plus half of dx. I'm not going to, dx is infinitely small, so I don't have to worry about that. I can just say that this distance is x. It's a little bit different when we do y sub c, so that's why I'm pointing this out right now. So now I've got this equation. I know I actually have a value for y of x. So x sub c equals the integral from 0 to 3. X is just the distance from the y-axis to the centroid of my little integral strips, which is always going to be x, where x is going to go from 0 to 3. Y of x is 3x squared plus 5 times dx. And then my denominator, integral from 0 to 3. Y of x is just 3x squared plus 5. I'm just subbing in the equation times d of x. So those look like things I can probably integrate. Let's see if I can do that. Let's go in MathCAD and do that. Obviously, these are easy enough that we could integrate by hand, but I wanted to do them over here if we can. So we'll see if I can figure out where that definite integral is. Right there. All right, so we're going to go from 0 to 3, and we're going to integrate x times the quantity 3 times x squared plus 5 dx. That's part of it. We have some more though. So this is going to be x sub c. X c equals this guy. All of that, whoops, not all of that, all of that divided by the area, which we can put another definite integral, 0 to 3, whoops, wrong place for the 3. Well, actually, that we do need a 3 there. 3 times x squared, whoops, that's not squared. Plus 5 dx. 1.982. Okay. If I look at this little guy, do I believe 1.982? Let's go to our picture over here. It's a little bigger. 1.982. So the centroid of this entire shape, let's draw it this way, looks like if I were to cut this shape out of the piece of plywood, thin plywood, and try to lay it down flat and balance it on something, I'm thinking it's going to balance, I don't know, right in there somewhere, right? Because I've got more, maybe even further to the right. Well, whichever way is right on your screen. So what this is saying is that x sub c, this distance, was I've already forgot it, 1.982 units, whatever the units are. And I could believe that. There's 3 over here, and there's 0. So 2, 1.982 is more or less 2. Looks like where I would predict it to be. So that seems reasonable to me. So this is one way you could do it. Let me point out one thing about y sub c. We don't need to calculate y sub c, but I do need to point out one thing about it. So y sub c equals integral y dA over integral of dA. So we can do the same thing with dA, right? So integral of y times dA was y of x times dx over integral y of x times dx. So the little catch that's going to throw people off on doing this is not y of x. We have to go back to what that y meant originally. So we didn't really draw it, but that y was this distance. And just drew right through the thing there. So that's y1. So it's the distance from the x-axis to the centroid of my individual little component. In this case, it's a sphere. In this case, it's this little differential strip. So this, oh wow, I clicked the button. Not there. There. This value, where can we put that? Right here. You shouldn't ever do this, like draw a leader line to a leader line. That's kind of weird, but that's what we're going to do. Or these aren't leader lines, these are dimension lines. Dimension line, using a dimension line as a leader line is not proper, but it'll get the point across for here. So this y is what we're talking about. So that's not y. That's actually, or that's not y of x. That's actually y of x divided by 2. So that's going to catch people if you're not careful, because it looks like, well, there's a y. That's also why I wrote y of x for that other one, because that y of x actually is the height of the square, or the little differential strip that we drew, the blue one. And this y is not y of x. It is the distance between the centroid of the strip and our reference axis. So this is really integral 0 to 3 again of y is y of x over 2 times y of x times dx over integral. This is just y of x here. So that will potentially create problems if you go to do this and you don't recognize that. If you don't want to do that, you could create differential strips that are horizontal, and then you wouldn't have to deal with that on the y, but you'd have to deal with it on the x. So just, you're not often going to have to do this part. Maybe never, maybe on homework, but like in real life, you probably won't have to do this very often unless you do run into one of those weird, like your beam really does have to be some kind of weird shape like this that's defined by a function and not just a rectangle or whatever. Then at least maybe you'll remember this and you can go look it up and see how to do it. What you do most of the time is you do this. So let's go over to where? Here. So you look at something like this. Oh, well, we can't do that then, can we? There we go. A chart that has various shapes and the location of their centroid. Now, obviously, these are not the only shapes. In fact, there's one that kind of looks like what we did, right? I don't know that that equation is... Oh, it's kind of off our screen. Let's move him over a little bit. There we go. I don't know if that's the same equation that we had, but it is similar. But here's a couple of shapes. Be careful with it. So we got some 3D shapes. We're not really doing those. These three over here are not solid shapes. So the three on the left-hand side of the page are like you took a wire. I don't have a wire laying around here. Here's one. Like you took a wire and bent it into that arc. So you might need to know that at some point. But be careful with this one, circular arc, quarter circular arc, and semicircular arc. They are not solid shapes. They're a wire that's bent into that arc. All these that are shaded in, those are the ones that we'll end up using. They're still limited, you know. There are not that many shapes there. There is a rectangle, and then some pieces of circles and some pieces of triangles. But that's probably not all we need. So what we have to do is figure out how can we take these common shapes that we have. All of those had equations on them. You might not can see them. We'll have to zoom in. There's a rectangle. There's some equations for a rectangle. There's x sub c and y sub c. They even give you the area of a rectangle if you need that. Some of these you might need the area for, like the area of a quadrant of an ellipse. You may not know that offhand. But they give you these. So we need to be able to take these, arrange them into whatever pattern we're going to use to create our cross section and combine them together. And so that's what you do most of the time, instead of doing the equation version like this guy. This is handy and it's good to know what's going on, but a lot of times what you actually do is you combine shapes together that are pre-solved. So let's do that. Let's do the simplest one that we can do that combines shapes. That's not, you know, like we could just pick one that's straight out of it, like a rectangle or a square or whatever, but let's create something new. So let's see, is there one more? That and that. All right. So we have made a T-beam. Let's see if we can find a picture of a T-beam. Let's see, where did my... Those are not T. Well, this is a T. It's upside down from what we drew, but there's a T-beam, right? It's got a little, here's kind of what I drew. So it's got a top flange on it and a, in this case, vertical stem. So those are the terminology that we'll need later on. Just so you know, here's an I-beam. Whoops, don't know why I did that. Shaped like the letter I. A lot of these, not all of these, a lot of these are kind of named after what their cross-section looks like. So that's like a capital letter I. The T looks like a capital letter T. Now, a lot of times these beams like this might be a W. And the W is understood to be wide flanged I-beam. This one right here might be an S, standard flanged I-beam, because it's a little bit narrow. The flanges are the top and the bottom. Let's see what else we have here. These are all I-beams. Well, we'll look at well, let's look at a channel beam. Oops, channel beam. Channel beam. Here, there's a channel, so it looks like the letter C. You know, kind of laying on its back right there in that picture. So there's a lot of these beams. They we'll get more into the beams and beam designations later on when we deal more directly with beams. For now, we just want to take some kind of shape, in this case a T, and figure out where the centroid is. So this is more like the cookbook approach to doing it. So let's do this. We have to dimension this thing so that we can figure out where the centroid is. 1, 2, 3, 4, 5, 6, 7, 8. That's 9. Let's just call it inches. Let's call this 10 inches just so we don't have another 9. Or is that 8? 1, 2, 3, 4, 5. That's 8. We'll do 8. And then let's do 1 inch would be really thick for one of these things. So let's say that the stem here is a 1/2 inch, and let's call the flange 1/4 inch, just so we have different numbers. All right. And like I said, on a book problem, the reference point would be given to you. Now, if you're just doing this on your own, you can pick whatever reference you want, but I'm going to put our reference axis here for X, and right through the middle for Y. Okay, and our goal is now just doing it this way. I can see that the centroid should be, I don't know, right here. So there's symmetry about the y-axis. So x sub c, just by observation, x sub c equals 0, just by looking at it. Y sub c, when I have these discrete pieces like this, the ones that match up in my chart, the integral stuff doesn't make as much sense at that point, but these summation equations kind of make sense when I've got discrete blocks. So if I want to know y sub c, I can take this y sub c discrete equation and use it. So let's do that. So y sub c equals the summation of ai times yi over summation of ai, right? So what I usually like to do is go in here and kind of mark out where the, well, first of all, pick which part is number 1 and which part is number 2. So I'll call this part 1 and this stem part 2. Find their centroids. So there's the centroid of part 1, and there's the centroid of part 2. And let's just write the equation this time. And then on the next one, I will show you more of a like Excel type sheet that you might build by hand or in Excel. I had Excel open, so maybe we'll do it in Excel. This one we'll just write out by hand. So the summation of a times y. So I take the area of part 1, which is 9 inches times 0.25 inches. And I multiply times the y coordinate of its centroid, which is that distance. So that is 8 plus 0.125. So 8.125 inches. So I know that because in this case I'm dealing with rectangles, which where are little, I think it's on this one. There. I know that the y sub c, let's get even closer. Y sub c for a rectangle is right in the center. So you probably don't have to look that up, but they do tell you that Well, y sub c is the height of the rectangle divided by 2. But I'm not measuring from the bottom of the rectangle, part 1. I'm measuring all the way down to the x-axis. So that's why I had to add another 8 to it. So 8.125 inches. So that would be A1 times Y1 plus, because I'm doing a summation, A2 is 8 inches tall by a ½ inch wide. And that's the area for part 2, the stem. The Y for part 2 is this distance all the way down to the x-axis. So that's 4 inches. So multiply that times 4 inches. And then the denominator is just the total area. So it would be 9 inches times ¼ inch plus 8 inches times a ½ inch. And whatever the math comes out to that to be would give us our location for y sub c. I don't have a calculator that's handy right here. So let's just, I guess we'll put it in MathCAD. There's MathCAD. All right, so I might have to, let's see. How are we gonna, maybe I'll move this over here so I can look at it and put it in MathCAD. All right, so I've got, these are all inches. I'm gonna leave the units off just to make it faster to put in MathCAD. 9 times 0.25 times 8.125 plus 8 times 0.5 times 4, oops, divided by 9 times 0.25 plus 8 times 0.5. 5.485. And those would be inches in the units. So let's get this back where it was. Somewhere there. So 5.485. So what that says is that if I measure from that same reference, the same reference that I measured all the other things from, I go up 5.5 inches. So 1, 2, 3, 4, 5.5. So I was a little off. It says that the centroid for it is right there. So right in there somewhere. And that distance is 5.485 inches. So that's how we would use the predetermined, data here, these equations for location of centroid. I did pick the most simple one. There are clearly more complicated ones to deal with. But for our first example, this little guy seems like it would be good. Okay. What time are we at? We have plenty of time. I don't see any questions, so we're going to carry on. And let's go grab a web work problem, one of the optional ones. Maybe I've got, well, yeah, there's one. That's one I picked out. All right. So this is just a web work problem, optional 1, problem 21. All right. It asked me to find x sub c and y sub c. And it's got more than just rectangles. In fact, it's got a hole in it too, so that we'll have to deal with that. So let's copy this picture. Actually, let's just copy this so that we get our numbers in there too. Go over here, plop it down, and maybe make it a little bit bigger. Not a whole lot bigger. All right. So what we have to do, this one gives us our reference axis, so you can see those on there. I'll just overlay them. There's X and there's Y. So all of our measurements need to be made from those reference axes, or at least translated to them when we go to plug them in, down here somewhere. So the problem, the homework statement, exam questions, they're going to have some reference already given, so that when you put your answers in, everybody's in agreement. Because it could be like, I look at this problem, might want to put the origin way down here, and somebody else puts it in the middle where we've got it here. Somebody else puts it on this corner. So we have to agree on where the reference is, otherwise we won't all get the same numbers. We'll get the same location, but it'll be referenced differently. All right, so I've got to figure out how am I going to divide this into pieces that I have, where's the thing that I have to work with. So there's a quarter circle. I saw that in there. There were rectangles. They might have been squares, but they were in there. This picture, for whatever reason, it has a rectangle, but it doesn't use a circle. It doesn't show you a circle, but you could also use a circle. All right. So let's start dividing this up. I'm going to say that I'm going to use two rectangles. So this piece right here, let's see, maybe, oh, get off there. You know, this guy. Now it's going to cover up some of that hole. That's okay. That's part one. Part two, we'll make this blue color. And it'll be this quarter circle also covering up part of that hole, which is okay. Part three, we'll make red. It'll be this rectangle. I do have triangles in my little chart. Let's see if I can find another color though. There's gray. I don't know if that'll show up, but part four will be a triangle right there. And then part five, I'm going to have to cut away this hole in the middle. So that'll be part five. It'll actually have a negative area because I'm cutting it out. All these others are positive areas with a little yellow, that's supposed to be a 5 in the middle of it. Part number 5, it's actually a negative area because it's like I built the solid shape out of the green, blue, red, and gray shapes, and then I cut away the yellow circle in the middle. So this, you could use the same approach. Just write it all out in the equation, it'd be fine. It gets a little long, the equation does. So I'm gonna show a different way to do this same thing that's more of a bookkeeping thing. That's where Excel comes in. I'm gonna draw it out by hand, but maybe we'll plug it into Excel to do the calculations. All right, so what I want to create is a little table. And over here I'm gonna have part number. So I've got 1, 2, 3, 4, and 5. And then I usually go in just for my own self and kind of draw a little picture of what each of these parts is so that I can kind of keep track of what's what. So those are my parts. So in my equation, one of the things I need is the area. I need the area to multiply times x and y, and I also need the area to calculate the total area. So I'm going to put the area, my units will be in square inches, and I just go and calculate the area of each one of these things. So I really need a calculator now. Let's see, maybe this one will work. Maybe. So B times A for part 1. So 6.3 times A, 7.6. So 47.88. The quarter circle. So I've got a radius of A, so pi, radius squared, which is 7.6. But it's a quarter circle, so I need to divide it by 4. Well, that doesn't look right. I must have typed something in wrong on one of those. Something's definitely not right. Let's see. Let's look at A again. Oh, no, that could be the problem. And then that's better. 45.365. And then I've got the red one, C times A. So 7.5 times A of 7.6, 57 exactly. Then I've got the gray triangle, which is B times C divided by 2. So B is 6.3 times C is 7.5 divided by 2 because it's a triangle. 23.625. And then I've got the hole in the middle. So it's a negative area because it's being cut away from these others. So minus pi d squared over 4. So D is 5.1. Pi over 4. So I think it ended up being 20.428. So if I take and I sum that column, I will have the total area, right? So we'll do that. Well, let's do that now. 47.88, 45.365, 57, 23.625, and 20.428 subtracted. So if I did it right, 153.442 square inches. That's point. Okay, so that would be the denominator in my equation up here. Also, now if I have, let's just do, I don't know, x sub c. Measure in inches. So this is where I would go in and let's mark the centroid for each part. And the circle looks like it's right there on the middle. All right. So what I need in my table that I'm creating over here is the x coordinate of each of these centroids. So for the green piece, it is in the negative x direction. So it's actually a negative here. Negative b over 2. So 6.3 is b. So 3.15. For 2, it gets a little more complicated. So 2 is this distance right here. That is not half of A, like it was for the rectangle. The rectangle is pretty easy because I know that the centroid's right there in the middle of it. For this thing, I've got to go to my little chart. So I've got to find a quadrant of a circle right there. And it says that the distance from the centroid over to, in this case, the left side of the quadrant, which is exactly what I need right here. Sometimes it's not. Sometimes this quarter circle could be moved around somewhere. And so you have to be careful. What goes in this chart on the screen right now is the distance between the reference axis and the centroid. What's on here is the distance between this axis, which is shown on this picture, and the centroid. So sometimes you have to rethink what these equations are telling you. But here, that distance is labeled xc, 4r over 3 pi, where r is the radius of that circle, or, well, the quarter circle. 4r over 3 pi. So 4r over 3 pi. For the radius is a 7.6. Divided by 4r over 3 pi, so divide by 3 and divide by pi. So 3.226 is that distance, and it's positive. Oh. Okay. The red one, now I'm back to a rectangle, so it's just a over 2. 7.6 over 2 is 3.8. Is positive. The triangle, another one of the negative ones, another one you may not know the distance for, This one's even a little bit more tricky, although it's a simpler equation. There's our triangle. Now this triangle is not rotated the same way that this triangle is. So I have to be careful about what distance do I want to know. I want to know the distance between the reference axis here and the centroid here. So I want to know that distance. So I need to find on this chart that distance. I'm going to say that it's labeled as y sub c. You know, that looks like what I need. Even though I'm actually calculating an x distance, I need the distance between the centroid and that side. So that's y sub c, which is h, the height of the triangle, over 3. So I'm going to take b over 3 as that distance, but it is negative. So minus b is 6.3, and divide that by 3, 2.1. So that might take a little bit of like mentally figuring out how you're rotating that triangle to match the one that we have here. You just got to figure that out. The circle, its x sub c is 0. It's like right on the origin, so that's easy. 0. Now my equation says, I've already calculated the denominator, right? I don't remember what the number is, but I calculate it's 153.4. Now I need to calculate this numerator part. I have individual a's, I have individual x's. I did the x one, so I'm not doing y right now. I'm doing x. So I did the individual x's. So I need to create a column that is a times x. It'll have units of inches cubed. It's not a volume, but that's, you know, inches squared times inches would be inches cubed. So 47.88 times negative 3.15 is negative 150.822. 45.365 times positive 3.226 is 146.347. It is important to keep those negative and positive signs in there, though, because that matters. Okay, 57 times 3.8, 216.6, and 23.625 times negative 2.1 is negative 49.613. Anything times 0 is 0. If I sum that column, I will have the summation of ax equals, and that's the numerator for my equation. So x sub c equals summation of a times x over, that should be times x, summation of a. I've got the summation of a, 153.4 inches squared. Let's add these things together. So negative 150, how do I put a negative sign on here? There we go. 0.822. 146.347, need to add that. 216.6, add that. 49.613, subtract that. I think 162.512 inches cubed, which is going to go right here. And we do that math, so divide by 153.4. And it says 1.059 inches. So inches cubed over inches squared is inches. So the moment of truth is when we plug this thing into WebWork. I'm not even sure where WebWork is right now. There it is. What was it? 1.059. Inches are already there. Let's check our... Well, first let's check and see if that makes sense. So one thing to note on exams, WebWork, all of these problems where you get dynamically assigned values for the dimensions like A, B, and C, and D, is that that picture is not regenerated for your particular dimension. So the picture is very generic. So in my picture, B looks about the same as A, but in my units or in my actual dimensions, B is 1.25 inches larger than A. So, but it doesn't actually update your picture. So just looking at the picture, you can only get so much information. You would have to actually go redraw it to scale to really figure out if what you're doing is looking correct or not. But I could believe at least I didn't get like 10. Like if I got 10, which is not even on my picture here, that I would know is wrong. 1 puts it somewhere over here. I can kind of believe that. So let's see if WebWorks says we're right. Submit answers. Oh, we got to log in. Hey, we did. We got it right. So good deal. To do the y sub c, which is, at this point it's getting a little redundant, but just for the purpose of showing you what you would do, I don't know if we'll calculate the number. Maybe, I don't know. Maybe we will. I don't know. I want to put it over here, but ran out of room. Oh, I bet it's off the bottom of my screen. Yeah, there we go. All right. So A, oh no, we already have A. We need y sub c. Also in inches for each individual part. So let's see if we can kind of get the parts back on the screen. There we go. So this is measured from the x-axis. So part 1 would be half of A, which is scrolled off. There we go. A is 7.6. So 3.8. Part 2 is that same deal. It's actually the same exact number. So if we go to our picture, find our quarter circle, x sub c and y sub c, they're the same thing, 4r over 3 pi. So it's going to be the same as it was for x sub c, 3.226. 3 is below the x-axis, so that's negative. Half of c, so 7.5. Half that, 3.75, but make it negative. The triangle, it's actually the same also, and as it was before, because now I just need this dimension, which is also 1/3 of the c dimension. So actually it's not the same. The other one was 1/3 of the b dimension. This one's 1/3 of c. So c is 7.5. A third of that is 2.5. Yeah, 2.5. And it's negative. Oh, let's make it the right color though. This one's the same. The circle is still in the middle, so it's 0. Now, scroll over a little bit. We make us a column. See, this is where I was saying it could be beneficial to do these in Excel. The problem with Excel is, for one, you don't have Excel on the exam, so you can't do that on exam. The other problem with it is, your calculations are hidden behind the cell. So I guess that's no different than what I'm doing here, because you don't even see my calculations. But it can get stuff embedded in there that's hard to track down. But it would do your math right, at least. So A times Y, we have 47.88 times 3.8, 181.944, 45.365 times 3.266, 148.162, 57 times negative 3.75, so negative 213.75, 23.625 times 2.5, negative, so negative 59.063, and a 0 here. Do our summation of A times Y, 181.944, 148.162, 213.75 subtracted, 59.063 subtracted. So 57.293. And then I could do y sub c equals 57.293 inches cubed over 153.442 inches squared equals 0.373 inches. So a positive is what it came out to be, just floating above, which does make sense because there's a little more area on top. Remember, I'm thinking about this coordinate would be where this would balance. Now, it actually ends up kind of, right in here, well, right over here, I think, where there's a hole. So it couldn't actually, you couldn't physically balance it on that hole. But if there was something there, you could balance it there. So it's not really about balancing it. That's just a way to visualize it. Let's see if this number is right. In here. 0.373. No, oh, 36. So I could have made any number of tiny errors. Let's see if any of them are obvious here. 1 is half of A. That's right. 2 should be the same as that. 3 should be half of C. 3.75. Wait, C is 7.5. Yeah, there's 3 and it's negative. And then a third of C would be 2.5, so that seems right. I wonder if I did some multiplying wrong over here. That one seems right. Oh, I did do. All right, so I might have multiplied this number wrong somehow. All right, so 45.365 times 3.226 is 146.347. Let's just check the others while I'm here. 57 times 3.75. That one's right. 23.625 times 2.5. That one's right. All right, so let's do our summation again. So my new total is 55.478, which would be 0.362. So made a little mistake there. Oh, well, now we're just down into, it's 0.361 and I got 0.362 because I didn't show enough decimals on my calculator. So that's all that is. I just didn't, I need to show more decimals. Let's see. Yes, I actually have 0.361 556809739. There we go. So that's just a WebWork deal. All right. So that's kind of the idea. I opened up some homework. Now you'll notice, let's actually look at that. You'll notice that homework 11, this is homework 11 for the Centroids. 9 and 10 have much later due dates, like in July, the end of July. So we are skipping 9 and 10 for now, just on the order of our topics. Those are frames and machines, which we won't talk about until after exam 1. So it is correct that you skip from homework 8 to homework 11. That is correct. All right, I will see y'all Monday, and we'll continue talking. We're actually getting close to the end of topics for exam 1, I believe. This might be the last topic for exam 1, in fact. So we'll see you on Monday.